For this lesson, we're going to be introducing the idea of trigonometric identities. This is a topic that a lot of students either look on in fear because of what their predecessors, what other students have told them, or they tend to regard it with some level of discomfort because of the one thing about identities is there often is not a clear set of instructions on what you need to do. Identities are something of a solving a mathematical puzzle. But if you practice and if you just are willing to explore different ways of doing something, then hopefully you will find, as maybe not the majority, but many math students and certainly the majority of math teachers actually quite enjoy trigonometric identities. We're going to be starting at a very fundamental level with this lesson. First of all, what do I mean by an identity? An identity is when you have some sort of equation where um, the left side is equal to the right side for all possible variables, or sorry, all possible values of the variable, or all valid values of the variable. Now in this case, this one is an algebraic identity, which basically this says anywhere that I have x plus 1 all squared, I could replace it with x squared plus 2x plus 1. So if I had an expression, let's just make something up. If I had y squared plus x plus 1 all squared plus z squared, I could change that if I wanted to into y squared plus x squared plus 2x plus 1 plus z squared. And of course, this seems almost painfully obvious because we know algebraically that x plus 1 all squared is the same as x squared plus 2x plus 1. But you can use identities where once you either know the identity, you've been told it, or in the case of this lesson, I'm actually going to show you where some of these identities come from, then you can make that exchange, and the exchange is not always obvious, but it can be quite useful. In order for us to do this, we're going to be making use of the more generic definitions for sine, cosine, and tangent. And the reason we're doing that is because we want our identities to be valid for all values of the variable. And the variable in this case is going to be focusing on the angle theta, but it also needs to include the coordinates, the x and y coordinates of a point, and then the r value, which is the length of the terminal arm. So we need to work with these identities in the most generic way possible so that we satisfy the fact that these identities will be true for all possible values or all valid values. So let's go ahead and start off with something that's known as the quotient identity. So I've asked you to consider sine theta divided by cosine theta, and then I'm going to rewrite this as an equivalent expression. What is sine theta? Sine theta, using our definition in the Cartesian plane, is y divided by r. Cosine theta is x divided by r. But I can rewrite that. I have a fraction divided by a fraction. I can rewrite that as y divided by r multiplied by, I multiply by the reciprocal of the denominator fraction, and that gives me r divided by x. The r's divide out and just become equal to 1. And so overall, I end up with y divided by x. But y divided by x actually is a definition that we already know. Y divided by x is actually tan theta. So our first identity is that the ratio of sine theta over cosine theta is actually equivalent to tan theta. And there is your first trigonometric identity, which is known as the quotient identity because we took the quotient of sine and cosine. That means wherever I have sine theta over cos theta, I could replace it with tan theta. Wherever I have tan theta, I could replace it with sine theta over cos theta, if either of those replacements would be useful to me. Now, something before I move on here, because I'm about to make use of at least one of these conventions. The first one is the use of brackets. You do have to be careful about how you write these things. For example, if I have the sine of x plus 2, I don't want to write it this way, sine x plus 2, because sine x plus 2 written this way looks like you're taking the sine of x, and then when you're done with that, you're adding 2. Whereas the original intention here was to take x and add 2 to that value, and then take the sine of the overall result. If the argument of sine or cosine or tangent is obviously a single term, for example, in this case, 25 degrees, there's really no way to interpret this that doesn't involve taking the sine of that whole value. There's no way to break that up that could be confusing. The same thing is true here, cosine of x, tangent of theta. So you don't need to use the bracket every time. If you want to use the bracket every time, no one is going to criticize you if you want to write these this way. There's nothing wrong with that. But if it's clear, you don't have to use the bracket. Now that is not the convention that I'm going to make immediate use of. It's this second one. From a mathematical point of view, one mathematical convention that is accepted is that if we have, for example, the sine of x and we want to square that. So in other words, if we had the sine of x multiplied by the sine of x, that could be written as the thing in the brackets, which is sine of x, all squared. That's, by definition, that's what it means to square this. But there's another convention that we use, in particular with trigonometric functions, which is we apply the exponent between the function name, in this case sine, and the function argument. And this is read as sine squared of x. So it's a function notation. Sine is a function. So this is the function squared, and then the argument, the of x, means of that particular argument. Now, there's an exception to this, which is if we want the inverse, and we've already been working with this, we use a -1 in that location. So this is now the inverse cosine of theta. If we wanted the exponent to be a -1, then that is the one exception where you must write it using the bracket notation. So in this case, you mean the reciprocal. You want the exponent to be -1. So the cosine of theta all to the exponent, -1, is the same as 1 over the cosine of theta. This is a pretty confusing convention until you get used to it. Once you do get used to it, it becomes second nature, but you do have to give it a little bit of time. And you can see here, this is why I wanted to bring it up, because this Pythagorean identity is typically written this way, sine squared theta plus cos squared theta. Let's go ahead and rewrite that, being careful. So this is the same as, you know what, I'm going to put an extra line in here that I wouldn't normally bother with, but in case people are not completely comfortable with the convention that I just wrote, here's a reminder. Sine squared theta is the same as sine theta all squared. Cos squared theta is the same as cos theta all squared. But sine of theta, the thing in the brackets, is defined as y over r, and that's all squared. Cosine theta is x over r, and that's all squared. So there's a couple of ways you could approach this, but I'm going to try to be as straightforward as I can. So y over r all squared is the same as y squared over r squared plus x squared over r squared. Notice I already have a common denominator of r squared. So this just becomes y squared plus x squared over r squared. I don't need to do this extra line, but I'm going to reorder that to be x squared plus y squared over r squared. And the importance of this is that our relationship for r squared was defined as the length of the terminal arm can be written in terms of a hypotenuse. So r squared actually turns out to be x squared plus y squared, which means this is actually r squared divided by r squared, which is equal to 1. And so now we end up with the Pythagorean identity says that sine squared theta plus cosine squared theta is equal to 1. So that identity is one that, for those of you who, well, hopefully just for this class you'll remember that, but for those of you who go on to use or to continue to study mathematics, this will be something that you will have memorized. You'll see it so many times you'll have no choice. You can rewrite this. Sometimes we need to manipulate these into a different form. So you might also make use of the identity that sine squared theta is the same as 1 minus cos squared theta. That was just me subtracting cos squared from both sides. Or you might write it as cos squared theta is 1 minus sine squared theta. And depending on what it is that you're provided with, one of these three identities, they're all based, of course, off of the main Pythagorean identity, one of these three different forms may actually be the thing that's useful to you. Now, that's it. Those are the identities that I'm showing you for now, just the two, just the quotient identity and the Pythagorean identity. When you're trying to prove an identity, proving an identity is to establish that the left side is equal to the right side in the equation. A general strategy, start with the most complicated side and make it easier. It's actually easier to do this than it is to start with a simple side and make it complicated. Because when you start with something simple and try to make it complicated, you can go in so many different directions that you might not go in the right direction. It's almost always a good idea to use the quotient identity, especially when you're new to this. Express the quotient identity in terms of sine and cosine. Sine and cosine are kind of like your building blocks for trigonometry. So if you can express everything in terms of sine and cosine, you're on the right track. 2 and 3 kind of go together, because if you're expressing tangent, you're using the quotient, and then once you've got everything in terms of sine and cosine, maybe you can use one of the three forms of the Pythagorean identity. And then finally, only work on one side at a time. You can switch sides if you need to, but I usually only recommend you do that if you kind of get to a roadblock on one side, then see if you can work on the other side. Some teachers, some instructors may insist that you only work on a single side. If I feel like I have time, I'll show you what that looks like in this lesson. Okay, let's start with this one. You can see here's the left side and here's the right side. I'm trying to prove that the left side is equal to the right side. There's a very specific form that a proof like this should take, at least based on my understanding of math and from what I've both received in instruction and what I've seen in reputable textbooks. Now I say reputable textbooks because I've seen textbooks that don't follow this convention, and I really don't know what to think about that. So I'm going to follow what I consider to be a fairly rigorous convention, which is you must refer to the left side and right side separately. So the left side here is tan theta cos theta. The right side here is sine theta. My goal is to show that these two things, my goal is to independently of each other show that these two things are equal. So it's not working with an equation where what I do to one side I do to the other side. It instead is I'm working on each side independently. In this case, the change I'm going to make, I'm going to follow my advice. I've got a tan theta here, which I'm going to replace with sine theta over cos theta, multiplied by cos theta. Now this one's fairly simple because once I make that change, you can see that cos theta goes into cos theta once, cos theta goes into cos theta once, and I end up with sine theta. And of course, this is equal to my right side, which is listed over here. Therefore, left side equals right side, and you have proven. Your therefore statement could be, you could also say, therefore, tan theta cos theta equals sine theta. That would be a valid therefore statement. Or you might say, therefore, identity is true, or you might use the word valid. Something like that. All right, let's go for something a little bit more sophisticated. My left side is equal to the tan squared of theta. My right side is equal to sine squared of theta cosine to the -2 of theta. So let's go ahead and make this replacement. Tan squared of theta. I'm actually going to rewrite this. Again, I don't think you should need to do this once you get used to it, but I'm just going to remind you, tan squared of theta is the same as tan of theta all squared. And that is equal to something all squared, but instead of tan, I'm going to write that as sine theta over cosine theta. There's my replacement using an identity. That means I can square the numerator, which is sine squared theta, and square the denominator, which is cos squared theta. And this is a case where I could change this. I could actually finish this if I wanted to. But let's say you get to here and maybe you're just not super comfortable with things and you don't see it. You could now move over to this right side and then recognize that this is to the exponent -2. So this is saying cos theta to the exponent -2, which is the same thing as sine squared theta multiplied by 1 over cos squared theta. I'm really dragging this out, I know that. But sometimes you don't always see these things. Sometimes you actually have the two expressions, left side and right side, are equal to each other, but you don't recognize it. So you finish this off. Maybe now you realize, oh, hold on, this is sine squared over 1. This is 1 over cos squared. So I multiply numerator times numerator. I end up with sine squared theta. I multiply denominator by denominator. I end up with cos squared theta. Left side is equal to the right side. I have proven this identity is true. Okay, how about this one? Sine squared over 1 minus cos theta equals 1 plus cos theta. My left side is sine squared theta over 1 minus cos theta. My right side is equal to 1 plus cos theta. This is one of those ones that's actually, if you try to solve it as an equation where what you do to one side you do to the other side, it's actually easier, but that's one of the reasons why you cannot do it this way. So in this one, I'm going to explain to you why you can't do it that way. So let me go ahead and start this, and hopefully I will get an answer that makes sense. So the first thing I'm going to do is, well, I see I've got a sine squared theta, and this one is cosine. On my right side, I have no sines at all. So it might be a good idea to get rid of sine squared. Now to do that, I might, especially because it's sine squared, I'm going to just jot down the Pythagorean identity for you here. If I want to get rid of this sine squared, I can replace sine squared with 1 minus cos squared theta. So that's what I'm going to do here. Instead of sine squared, I'm going to write 1 minus cos squared theta. And this is where the puzzle part of this comes in, which is why some people like these very much, but a lot of people don't enjoy them because, well, how did you know to do this? I knew to do this partly because I just thought of in my head, well, what if I make that replacement? Can it take me anywhere useful? And if you don't see that, you can do trial and error. It's very inefficient, but it's how you're going to get better. Okay, now some people I think would get to this point and they would once again, they wouldn't know what to do. And that's because of this kind of strange form we're seeing things in. And to put this in a more familiar form, I'm just going to temporarily I'm going to say let x equal cosine theta. Now, I'm not going to recommend that you do this unless you really need to do it, but I'm doing it here because I want you to see, hopefully, I want you to see what I see when I look at this, which is I've got 1 minus x squared on top, and I've got 1 minus x on the bottom. 1 minus x squared is actually a difference of squares. 1 is a perfect square, and x squared is a perfect square. So this is actually the same as 1 minus x times 1 plus x, all divided by 1 minus x. And as you can see, there's an opportunity for me to divide out this factor 1 minus x. Now, I'm not going to do that yet. I'm going to replace it. Normally, I would just go ahead and do that, and then I'd go back to cosine. But in this case, I really want you to be thinking and seeing this so that you can actually go to this as your next line yourself. 1 minus cos theta, 1 plus cos theta, treating the cos thetas as a unit. And then that's all divided by 1 minus cos theta. You have to recognize that this 1 minus cos theta is a factor. So that entire factor goes into itself once. This entire factor goes into itself once. And I end up with 1 plus cosine theta. But 1 plus cosine theta is what I have here. So left side is equal to right side. I've shown this identity is true. Now, what is it that I was talking about the fact that this is a good reason why you're not allowed to work across the equal sign? In this case, I did my work starting on the left side and ending on the left side. I did all of my work going this way. Because I did not add, subtract, multiply, divide, I didn't cancel anything, I didn't divide anything out, I didn't lose any information from that right side, I didn't use any information from that right side. And so the work that I did here is what we call reversible. Okay, what that means is that I could start from here and I could actually work my way backwards to this original left side. And in order to do a proof of this particular type, it needs to be reversible. If you do something here, for example, let's say we did cross multiplication and you did a whole bunch of manipulation, you would have contaminated each side with the work that you're doing, and what you end up doing may, I only say may, it's not necessarily the case, but it may no longer be reversible. Okay, so that's it. I did a few increasingly difficult examples there, and then you've got some practice work here to hone your own skills.